Alright, our fourth day with limits. We're going to look at another fancy technique for finding limits at holes. But to start off, let's remember what we just did. So we're going to find limits of this. We want to rationalize that numerator. So we need to take the numerator, x plus 7 minus 2, over that denominator, 2x plus 6. And we want to multiply that by the conjugate of the numerator. So the square root of x plus 7 plus 2 over that same thing, x plus 7 square root plus 2, and we will get whatever's underneath the square root sign, so x plus 7, our a squared term, minus our b squared term, which is 4, over 2x plus 6 times that whole denominator, x plus 7 plus 2. Now let's simplify this further. 7 minus 4 in the numerator gives me an x plus 3. And in my denominator, notice 2x plus 6 can be factored as 2 times x plus 3. Oh, and now I still have my square root of x plus 7 plus 2. But x plus 3 cancel out, and I'm left with 1 over 2 times the square root of x plus 7 plus 2, and I'm gonna do that real quick. And whoa, that's ugly. Let's fix that. Still ugly. That's a 2 right there. And now let's rewrite this limit. And if you'll notice, the way I have this written right now is absolutely incorrect, because that should be in parentheses. If you forget those parentheses there, you will end up with the incorrect answer. So now that we're here, I can directly substitute in to get 1 over 2 times the square root of my x value is negative 3. Negative 3 plus 7 is 4, plus 2. Simplify this thing further. 1 over, and let's get rid of that. 1 over 2 times square root of 4 is 2, plus 2 is 4, so I get 1/8. My dog was crying a lot, so I had to let her out. So now we're going to look at a second technique for finding limits at holes. So to get us there, let's think about this. How would you write this as a single fraction, or how would you go about doing this subtraction problem? Well, we're going to find a common denominator. So if I multiply 2 by 4 over 4, I can get 3/4 minus 2 times 4. You can think of that 2 as a 2 over 1, and then you're just multiplying two fractions. 2 times 4 is 8 over 1 times 4 is 4, and again the whole point here is now I can write 3 minus 8 over 4, which is negative 5/4. Compare that to this problem, which is very similar. Except this time we do not have a 1 in the denominator of the second term. We have a 3, so now we are going to have to multiply twice. On the right here, we're going to multiply by the denominator of the other fraction, so 10 over 10. And on the left, we're going to multiply by the denominator of the second term there, so 3 over 3. And now I can simplify that. Let's go numerator of the first term. 3 times 9 is 27, over 3 times 10 is 30, plus, we'll do our second term now, numerator, 4 times 10 is 40, over 3 times 10 is 30. And so we have a common denominator, and now I can combine these and put them both over 30. So we get 27 plus 40 over 30, and so we can simplify that as 67 over 30. One more that we want to do here, same idea. We're going to have to multiply both by something, by the denominator of the other over the denominator of the other. So let's take x minus 4 for this fraction. So x minus 4 over x minus 4, and then let's take the 2 for this fraction, and now let's go ahead and multiply. 2 times 2 is 4 over, and I'm just going to leave this as 2 times x minus 4, plus 1 times x minus 4, well, that's just x minus 4 over 2 times x minus 4. Again, I'm just going to leave it as 2 times x minus 4 and simplify this further. The whole point was that now I can write this as 4 plus x minus 4 over 2 times x minus 4 as a single fraction. I could simplify this further. Notice I have a positive 4 and a negative 4 there. So they are going to eliminate each other, and we will get up x over 2x minus 8. That is the idea of our second technique, finding a common denominator. We will see why that is useful in a moment. But before we do, let's think about this. Dividing by number k is the same as multiplying by the reciprocal of k. Now what that means is if I have, say, 5 divided by 7, well, that is the same as 5 times 1/7. Dividing by a number is the same as multiplying by that number's reciprocal. The reciprocal of 7 is 1 over 7. You take the fraction and you flip it. So another way that's useful is if you have, say, 8 divided by 1/2. Well, dividing by 1/2 is the same as multiplying by the reciprocal of 1/2, which is 2. And so we could get 16 there. The point is, this will be useful. You will see why in a moment. Well, actually, now, let's look at this problem. Find the limit as x approaches 0 of this crazy looking function. Notice we cannot directly substitute in because we will get a 0 in that denominator there. But we can take a look at this numerator right there, and we can find a common denominator. And we actually just did that because this is the same problem as on the previous slide, or the 2 slides ago slide. Alright, it was actually 3 slides ago, but anyways, that numerator right there is the problem we just did over here, x over 2x minus 8. So I'm going to take that as my numerator, and now notice that is over x. So notice I have an x up top and an x in the super bottom right there. Well, let's think about how we could rewrite this problem, because we know that dividing by a number is the same as multiplying by that number's reciprocal. So if I take that uber numerator there, x over 2x minus 8, and instead of dividing by x, I multiply by the reciprocal of x, which is 1 over x, notice what I have. I have 2 fractions being multiplied together, which lets me think of them as one fraction with the terms being multiplied together. And so I have an x in my numerator and an x in my denominator. And so I have found my whole and I have removed them. Notice essentially what happened was that this x just popped up there and was multiplied by that whole term. Okay, so let's rewrite this now that we have everything figured out. The limit as x approaches 0 of 1 over 2x minus 8. And now I can directly substitute in 1 over 2 times 0 minus 8, which is negative 1/8. Let's do another problem here. Find the limit as x approaches negative 3/2. So again, let's give that numerator a makeover. We're going to want to find a common denominator here. So in order to do that, I'm going to multiply this 2 by x plus 1 over x plus 1. Then I will have my common denominator of x plus 1. So I'm going to get, well, maybe I'll leave that there, and we'll say limit as x approaches negative 3/2 of 1 plus 2 times x plus 1 over x plus 1 over 2x plus 3. And now I need to keep going because I don't yet see anything that can cancel out. but I'm rewriting my limit as x approaches negative 3 halves of, I can simplify that bit right there to, notice if I distribute this out, I'm going to get 2x plus 2, and I still have that plus 1 there. 1 plus 2 is 3, so I get 2x plus 3 over x plus 1 over 2x plus 3. And again, you can think that instead of dividing by that number right there, I can multiply by the reciprocal of that number, which is of course 1 over that number. And I have a 2x plus 3 and a 2x plus 3, numerator and denominator. So I get the limit as x approaches negative 3 halves of 1 over x plus 1. And I can directly substitute in negative 3 halves. Well, negative 3 halves equals negative 1.5. And negative 1.5 plus 1 is negative 0.5. So I really have the fraction 1 over negative 1/2. But again, dividing by a number like negative 1/2 is the same as multiplying by the reciprocal of that number, which is negative 2. So my answer is negative 2. Alright, one more to look at here. Same idea, except this time I'm going to need to multiply this bit right here by 4x minus 3 over 4x minus 3. And I'm going to need to multiply this bit by 3 over 3. And so I'm going to get the limit as x approaches 0 of 2 times 3 is 6, plus 2 times 4x is 8x, plus 2 times negative 3 is negative 6, so minus 6. Sorry for that little mental pause. And then I have that denominator, 3 times 4x minus 3. And I'm just going to leave it as 3 times 4x minus 3, just like that. All of this is negative over negative 8x. So let's take it one step farther. The limit as x approaches 0 of, look at my numerator, I've got a 6 and a negative 6, so I get 8x over that middle denominator thingy, 4x minus 3, all over negative 8x. And again, dividing by a number is the same as multiplying by the reciprocal of that number. So really I have 8x over 3 times 4x minus 3 times negative 1 over 8x. And notice what I did, I took that negative and I moved it to the numerator to help emphasize the fact that I have 8x and an 8x, since I pulled that negative 1 out. And I get the limit as x approaches 0 of negative 1 over 3 times 4x minus 3. And now I can directly substitute in 0 to get negative 1 over 3 times 4 times 0 minus 3. And so you get negative 1 over, that term cancels, I get 3 times negative 3 is negative 9. So we get a positive 1/9. And one more idea to talk about here real quick. I want to know, what is the easiest way to find this limit? Well, you may be looking at it and say, okay, well I have a fraction in my numerator, so I'm going to go ahead and find a common denominator and something will cancel out. Well, here's the deal. Yes, it does look like a problem where you would need to do that, but don't forget to check the x value you're finding the limit of, and negative 2 into that denominator does not make that denominator equal to 0, so I can plug it into that term, no problem. Negative 2 plus 5 also does not equal 0, so I have no problem directly substituting into this limit problem right here. Remember, if you can directly substitute in those terms, that is the easiest way to find the limit, and then we can simplify this down to this fraction right here. Negative 2 plus 5 is 3, so we get 1/3 plus 2/3 is 1, and so we get negative 1/4. So again, directly substituting in is the best method if possible. But let's quickly look at these limits right here. Notice the top 3 are filled out for you. We talked about this last unit. if the degree of the numerator is the same as the degree of the denominator, in each of these fractions on the top here, we have an x squared term in the numerator and the denominator, meaning our highest degree in both is 2. But it is saying the limit as x approaches infinity is, well, that's the idea of the horizontal asymptote, like we talked about last unit. When the degrees are the same, you can just find the limit as x approaches infinity to be that value there, the leading coefficient of the numerator divided by the leading coefficient of the denominator. And so we get all these values that we think we should get. In this case, we're going to get a 5 over a 7, so that limit is 5/7. And this limit is going to be this huge ugly number over this huge ugly number. But we didn't really talk about other possibilities. So let's think about the limit as x approaches infinity of this function right here. Notice that the degree of the denominator is 2 and the degree of the numerator is 1. And in this instance, again, if you think about these functions, think about a few x values. So imagine the x value of, say, 10. Well, in the numerator, we'd get 32, and in the denominator, we would get, what, 397? So that's a pretty small fraction when we're at the x value of 10 already. But let's think about maybe the x value of, ignore that, I can't talk and write at the same time. Let's think about the x value, say, 100. So if we do f of 100, we get 302 over 39,997, which is a even smaller fraction than 32 397ths by a large factor. And if we were to keep doing this and find f of 1,000 or f of 100,000 or million or whatever you want to do, add as many zeros and then keep adding them because you won't ever get to infinity. But that fraction is going to continue to get smaller and smaller and smaller. And so this limit is 0. If the degree of your denominator is greater than the degree of your numerator, the limit will approach 0. Alright, so let's think about this limit then. The limit as x approaches infinity of 2x plus 3 over 3x squared. Now, in this instance, notice the degree of the numerator is 1 and the degree of the denominator is 2. So we want to think about where this limit is going to go. Where is the horizontal asymptote going to occur here if we have one? Well, let's think about some values, some different x values as we get bigger and bigger. So f of 10 is going to be 23 over 299. So that's already a very small fraction, 23 299ths. Ooh, that's tiny. But compare that to, say, f of 100, which is a little bit bigger, but not so much bigger when you're thinking about infinity. Well, f of 100 is going to be 203 over 29,999. I don't remember where I left that off. But as you can see, again, we have another fraction that is very close to 0, and this time it is way closer to 0. So as I go bigger and bigger values, f of 1,000, f of 10,000, f of 100 billion, I'm still nowhere near infinity, but that fraction is so close to 0. The limit of this function is going to be 0. So if the degree of the denominator is greater than the degree of the numerator, the limit of that function as x approaches positive or negative infinity is 0. But let's compare that to the reverse situation. Well, imagine we had the reverse situation and we had 3x squared minus 1 in the numerator and 2x plus 3 in the denominator. Well, in this case, all of those values we found would be flipped. So f of 10, instead of being 23 over 299, would be 299 over 23. And f of 100, instead of being 203 over 29,999, would be 29,999 over 203. So in this case, instead of our fractions getting smaller, they're getting larger at a much, much, much quicker rate. Well, same rate really as before, but getting larger instead of smaller, that's the idea. And as we continue this off for bigger and bigger values of x, 1,000, 1,000,000, 10 billion, our fraction, the numerator of our fraction, gets so much larger than the denominator of our fraction, which means that our fraction is continuing to grow bigger and bigger and bigger, and this will happen forever, and so this limit will be infinity, positive infinity. But think about what happens in the other direction. Imagine when we're talking about negative values. Well, think about your function. This term is squared, so your numerator is going to be the same, except, so like for f of negative 10 and f of negative 100, we're going to have the same numerator because of that squared term there. It doesn't matter if your x value is negative, but your denominator does care if the x value is negative, and it's not going to change much about that value, but it will make it negative. So we'll have a positive number over a negative number. So if you talk about the limit as x approaches negative infinity, for this function it would be negative infinity. So compare that with this one. Notice this one we have a fifth degree function over a first degree function. Now if you think about this, pretend like that 2 wasn't there and you were just looking at 3x to the fifth over 7x to the first. Well, we could eliminate a power of x and change that to the fourth. And so really you're kind of talking about the function 3/7 times x to the fourth, and x to the fourth, we can think of this now as an end behavior function. And so when we know this function x to the fourth, to the right is up and to the left is up, so that tells us the limit as x approaches positive infinity is positive infinity. That's what that up is talking about. And the limit as f of x approaches negative infinity would also be positive infinity because it is also up to the left. If our coefficients were, say, maybe negative 3/7, or maybe the 7 was negative and the 3 was positive, then it would be the same idea, except it would be down and down. So both limits would be negative infinity. So let's perform one more task right here. We want to sketch the graph of this function f of x that satisfies all of these conditions. So we need to figure out what is happening at each of these various points, these various x values. So notice we got something going on at the x value of positive 1, positive 3, and negative 2. And then notice we have an infinite and negatively infinite limit here that we are looking for, which is going to tell us the end behavior of our function where we have a horizontal asymptote. So let's take a look at this and see what we know. The limit of f of x as x approaches infinity is positive 1. So that tells me out to the right I'm going to have a horizontal asymptote at the line y equals 1. Limit as x approaches negative infinity of this function f of x is 2. So out to the left, I am at a y value of 2 for my horizontal asymptote. The limit as x approaches 1 from the left is negative infinity, and the limit as x approaches 1 from the right is positive infinity. So that tells me at positive 1, I have a vertical asymptote. The limit as x approaches negative 2 from the left is infinity, and negative 2 from the right is also infinity. So that tells me at negative 2, I also have an asymptote there. And finally, if you look at the x value of 1, 2, 3, we've got a weird two-sided situation here where from the left the function is at the y value of 2, and the right it's at the y value of 4. So let's piece all this together. I'm just going to start to the left and work my way to the right. So the most leftmost thing that's happening is that I'm leveling out to the y value of 2, and then as I approach the x value of negative 2 from the left, my limit is positive infinity, so that tells me I need to look like that. As x approaches negative infinity, I'm at y equals 2, and as x approaches negative 2 from the left, I'm at positive infinity. And I also know that negative 2 from the right is positive infinity, so that tells me my branch is coming down there, my tails are together. And then the next interesting point is positive 1, and my battery is low and it paused me. We're looking at the x value of positive 1, and from the left my limit is negative infinity. So that tells me I'm down here, so I must be crossing over like that. And from the right at x equals 1, I am positive infinity. So my tails are apart. I'm coming up there. One last thing to look at the x value of positive 3 from the left, I'm going to the limit of 2. So when I hit positive 3, I'm at that y value of 2. But my limit as x approaches 3 from the right is positive 4. So that tells me that I have to be there and moving out to the right. But then I know that the limit as x approaches infinity is 1, so I level out to that horizontal asymptote. So that's what I should be looking at. Notice that over here I did two open circles because all we know is that the limit as x approaches those values are those values. But I don't know anything about the actual value of the function at that point. And so let's talk about the last idea for the day. What is a hole? What does it do to your function? And how does it relate to limits? Well, a hole is a removable discontinuity, so like x minus 4 over x minus 4 times x plus 3. It is considered a removable discontinuity because I could pull it out of my function and rewrite it as 1 over x plus 3 such that x is not equal to 4. These two things are exactly the same. It creates a gap at one specific point on the graph of a function, so everywhere else it is exactly the same except for at that one point where it does not exist. This is not this, I'm just drawing some random thing now. But it relates to limits because even though our function is not defined there, we can still find the value of where that hole would be. That is been so far our approach to limits.